So, Greg, thank you so much for coming to present to us today. And we know you came and joined us at the GSE conference one year, didn't you? And did a presentation for us, as I remember. So, welcome back to GSE, and the stage is yours, sir.
So thank you, Jamie. And yes, I did come over one time. Would love to come back and do it again. I just got to convince IBM to send me over. So for those of you that don't know me, I'm Greg Boyd. I spent a little bit over 30 years with IBM. Most of that time, I was a systems programmer for hire, working in what was kind of the predecessor to the Lab Services organization. But about the last 12 years of that career, I spent in the Washington Systems Center supporting the crypto technology that's available on Z. In 2014, I retired. I started my own company called Mainframe Crypto, basically doing the exact same thing, just doing it on my own, helping customers understand and implement the crypto technology that's available. 2 years ago, in the fall of 2021, IBM Lab Services reached out to me and invited me to come back to work. And I said, yeah, I'd love to, but I really don't want to work full time. I only want to work part time. And they were agreeable to that. And they were also agreeable to, I was going to continue to do work as Mainframe Crypto. But what I'm doing now is education and presentations like this, I typically do as Mainframe Crypto. The consulting work I do through IBM Lab Services. Now, that said, I am doing this session today as an IBMer, and I'll explain why a little bit further on in the presentation. So with that, let me get control here and see if I can page forward. So I want to start off by talking about just some background information to kind of level set people and to remind you that there are a lot of things that can impact your performance when we're looking at crypto. And so I want to cover a couple of those just to give you some background. And then we'll get in and look at some specific performance metrics that are available from IBM. And then lastly, a couple slides on the performance data, the reports that you can look at and maybe capture some information about what's going on with crypto. So this chart is one I use a lot in a lot of different presentations. When people typically think of cryptography, they think of scrambling and unscrambling of data. And it's actually a whole lot more involved than that. Within that idea, that confidentiality or scrambling and unscrambling of data, you've got two different kinds of algorithms. You've got symmetric algorithms and asymmetric algorithms. And they work very differently. With the symmetric algorithm, both parties use the same key. So I encrypt data with key 1. If I send you that ciphertext, you've got to decrypt that data with key 1. With asymmetric algorithms, we use two different but mathematically related key values. I can encrypt with one key, you would decrypt with the corresponding key. And those have very different performance metrics. And then within each of those, there are a number of different algorithms. Now for asymmetric, there's really three primary: RSA, Diffie-Hellman, and elliptic curve. And each of those has their own performance metrics. Within symmetric algorithms, there are actually hundreds of symmetric algorithms that are available. Each of those have their own unique performance characteristics. So that's a big variable in what you can expect. But in addition to scrambling and unscrambling of data, we also have the concept of data integrity, and that's where things like hashing and message authentication codes come into play. And they each have their own performance characteristics. Financial functions are basically just symmetric encryption, but they're very specialized symmetric encryption, focusing on very small blocks of data. And we're talking about ATM pins and protecting those. And then key security and integrity uses scrambling, it uses data integrity. All of those have their own unique performance characteristics. So you have to look at what you're doing in your environment, and every customer is going to be a bit unique in the mix that they have, and therefore the performance metrics that they can expect are going to be very dependent on what they're doing. So kind of one of the big points I want to make is when you're looking at performance in your environment, you have to know what your normal is, because every customer is going to have a different graph in terms of CPU utilization, number of operations that are being performed based on their own unique mix. On slide 4, the IBM hardware has historically been defined as either clear key hardware or secure key hardware. With clear key, your key material is going to exist somewhere in the clear, at least for a brief period of time. And if you go back to before hardware was available, if you implemented an algorithm like DES using software routines, that is using multiply instructions, shift logical instructions, your application would probably have a variable that says my key equals, and then some string of binary digits that's your key. And when you did that, that variable shows up in your address space, and anybody that can look at your address space can see that key. The clear key hardware expects to receive that key in the clear. So anybody that can look at your address space, or if you're using ICSF APIs, if somebody can look at the ICSF address space, they can potentially see your clear key in the address space. Secure key, on the other hand, relies on an HSM, or a hardware security module, that is tamper-resistant, tamper-responding technology, so that if somebody tries to put a probe on the card to see the key, the card is going to self-destruct and protect the key material. And when you're using secure key, you still have to store your key material maybe in a key store somewhere. Well, when you put it in the key store, you're only going to put it in the key store after it's been encrypted by another key, typically called the master key. So with secure key technology, you have a lot more security for the clear key, for the key material, but the trade-off is the way that that hardware is implemented, it's much more expensive in terms of performance impact, wait time, that sort of thing. And we're going to talk a lot more about that as we look at some of the charts later on. And then protected key is kind of a hybrid that combines secure key and clear key hardware. You've got one trip out to the Crypto Express card to rewrap your key material so that it's encrypted in the address space. It's just not always protected by that tamper responding technology. So the point here is, if you're, depending on what technology you're using, clear, secure, or protected, your performance metrics are going to be different. And then on slide 5, I talk about the hardware that's available. The functionality that's available in the two hardware devices is a little bit different. The clear key hardware, the CPAC-F hardware, is somewhat limited in its functionality, but what it can do very fast. The Crypto Express cards, on the other hand, they have a lot more functionality, but you have that performance impact of sending the work out to the Crypto Express card. And I need to point out that when you implement an API, your choice of an API determines what hardware is required. Jamie, I've got a pop-up on my screen that somebody's entered the waiting room. I don't know if you want me to respond to that or not.
Yeah,
thank you. And then those Crypto Express cards, they can be configured in one of 3 modes. By default, the card is configured in what's called CCA coprocessor mode. And when it's configured that way, you have all of the CCA functionality that IBM supports in the card. Alternatively, you can configure the card as what's called an accelerator. And when you do that, the card can only do 3 things. It can do 3 public key RSA operations, but it can do a boatload of them, a lot of them. So there's a trade-off here. You get, with more functionality, you get a little bit less performance. With less functionality, you've got a smaller operating system in the card and you get much better performance. And we'll see some examples of that a little bit later on. And then lastly, you can configure the card in EP11 or PKCS11 mode. When you do that, you get a completely different set of performance metrics because that PKCS11 architecture is very different from the CCA architecture. So once again, your configuration of your card is going to be a variable that comes into play when you're looking at performance in the crypto infrastructure. So with that, I want to start talking about some of the metrics that are available. And the first one I want to talk about, this tech doc was written probably 15 years ago. It's actually based on the Z10. And my partner at the WSC at the time, Ernie Noctegal, did some tests. We would often get the question, you know, does hardware encryption really help? And what he shows is yes, it really helps a lot. What he did was there was an old module software implementation of DES encryption called BDK DES. It was shipped with another IBM product, and you could encrypt data using single DES encryption by calling this software module. And what he did was he wrote a little program that basically just read a large file. I think it was like a 10 gig file. And it encrypted that file, and then he measured the CPU usage and the wall clock time that it took. And when he was running that software, he was able to encrypt about 500,000 bytes per second. But that was very expensive because that was being done on the general purpose engines, and that took almost a full CPU minute to encrypt that 10 gig file. Then he wrote an assembler routine that used the native CPACF instructions to encrypt the same file using the same DES algorithm and the same key. And when he did that using the hardware, he went from a 500,000 bytes to a second to almost 600 million bytes for a second. Tremendous improvement. And the CPU usage dropped from a CPU minute to almost nothing. It only took a couple of instructions to encrypt that full file. Then he did the same thing using triple DES, and you know, with triple DES, you're just executing DES 3 times. The throughput didn't drop by a third or to a third, but it was about a half of what it was with single DES encryption, and still the CPU time was only minorly, just a little bit higher. Then finally, he went off and did the same thing, sending the work to the Crypto Express cards using secure key technology. With DES encryption, his throughput, or the number of bytes per second, dropped to about half of what it was, but there was still a tremendous savings in CPU usage. So by offloading that work to the card, he got not quite as good a throughput, but still a significant benefit on his CPU. And the same thing with triple DES. The throughput was still lower, but the usage and the impact on his general purpose engines was minimal. So the point is, yes, hardware encryption does help. You want to use hardware encryption at every opportunity as opposed to using some software routines. Now, on slide 8, this presentation is based on a white paper that IBM publishes. William, in his earlier presentation on network encryption, he referenced this document as well. Every time IBM comes out with a new KEK, you know, Z14, Z15, Z16, they publish a performance of cryptographic operations document for that machine. Now, it typically takes a while. The Z16 has been out for a year and a half now. And IBM did publish this white paper a couple weeks ago. And I put together this presentation, actually did the presentation once. And then shortly after I did the presentation, IBM decided, you know, we need to bring that back and do further review. So the document that was published is no longer officially published. And that's why I'm presenting as an IBMer today, because as an IBMer, I'm allowed to talk about what's in the white paper. As Mainframe Crypto, since it is no longer published, I'm not allowed to talk about it. So The point is, this document will be available shortly when it completes its review. I've been told there aren't going to be any major changes. It just needs to go through that review. Now, one of the changes that they made in this document versus previous generations was they changed the definition of a megabyte. At one point in the previous versions of the document, they simply used 1 million. With this version of the document, they've gone back to the more standard 1 megabytes is 1024 by 1024 KB. So when you look at if you're comparing between machines, you probably need to take that into account. The other thing that they added in this new version is they do show a delta over the previous generation. So that's kind of handy. You can see, well, on the Z16, it's 2% faster, or maybe 0.1% slower, and we'll see some of those numbers a little bit later on. So the next set of charts are based on this Z16 performance white paper that, again, should be available shortly. On slide 9, what I'm comparing here is a couple of the modes for AES 256-bit encryption. Again, William talked about this in his network performance encryption session a little bit earlier. This document is comparing cipher block chaining to ciphertext stealing to Galloy counter mode operation. CBC has been around a long time. XTS and GCM are a little bit more recent. They both have their strengths, for example, and they both have their usages. Data set encryption, IBM's pervasive encryption, data set encryption relies on ciphertext stealing. The network encryption is relying more heavily on GCM mode, Galloy counter mode. So the performance characteristics are important. There's also impacts into how secure things are. Ciphertext stealing is much better for encrypting large blocks of data. It has some security advantages. So that's why they use both modes. And the point of this chart is to say that IBM has done a lot of work starting on the Z14, and it's been carried over into the Z15 and the Z16 to really improve performance with ciphertext stealing and Galloy counter mode, because those are used so extensively with data set encryption and with network encryption. Again, this is showing the native operations on the CPAC-F hardware. So invoking the cipher message instruction directly on the hardware, no API overhead, and we're using the fastest technology that's available. Which brings me to another point that I should have mentioned on the previous chart. This crypto performance white paper is designed to be a kind of a gee whiz document to tell you how wonderful the IBM hardware is. As one of my mentors a number of years ago put it, no customer will ever achieve these numbers in their site, because IBM has these test cases, these benchmarks are designed to show off the speed. In your environment, you're going to have lots of other things going on in the application. If you're encrypting data, you're going to have lots of other work that's going on there. You're not going to be able to achieve these numbers, but they are effective for comparison purposes. So when we look at things in the next couple of charts and comparing clear key to protected key to secure key, it will give you an idea of what you can expect from a performance perspective. Lastly, on this chart, we're measuring the number of operations per second, how many KM instructions we can execute with CBC mode versus XTS mode versus GCM. On slide 10, we've got the same information, but instead of presenting it as operations per second, is presented as megabytes per second. So basically, we're just taking the number of operations per second and multiplying it times the block size so you can see the performance. And the takeaway from this chart is that performance is much better with large block sizes. The overhead of sending 64 bytes to the CPAC-F hardware is the same as the overhead for sending 1 meg of data to the hardware. So if you can design your application to send large blocks of data as opposed to small blocks, that can help you with your performance. So for example, if you need to encrypt a social security number and a birth date and a name and an address, you could do 4 calls, 1 for each one, or to help with performance, what you want to do is maybe concatenate those fields together and encrypt them as a single operation. So that's going to give you better performance by sending more data in every operation. So those last 2 charts were for clear key operations. This is the same information, but using protected key operations. And again, this one is the operations per second. So obviously, just like on the previous operations per second, the larger the block size, the fewer operations that you can send at a time. But the throughput is still going to be better if you can do more data, larger blocks. And then on slide 12, we have the same information, but secure key, sending the work to the Crypto Express cards. Now, I'm going to compare these in a minute, but the point here is, once again, you've got more overhead to send work out to the Crypto Express card. You're effectively doing an I/O operation because the Crypto Express card is installed in the I/O cage. So you've got to get that work out to the card, then there's an asynchronous wait while the work is done on the card, and eventually the results are turned back. So the performance with secure key is significantly lower than clear key or protected key. And again, we'll see that more clearly in a minute. So the previous 3 sets of charts, we're talking about the hardware speeds. Now, on this chart, what we're looking at is if I use the ICSF APIs. So, for example, with ClearKey, instead of using the native KM instruction in my own assembler program, what I've done, the code is actually invoking an API that in turn ICSF will send the work to the CPAC-F hardware. So as you would imagine, because of the ICSF being involved, the numbers aren't quite as high as using the native instructions, but you have the advantage of now you have a much more portable operation. You're using the API. And you can use this. Instead of having to write an assembler routine, you can call these APIs from your COBOL program or your PL1 or from wherever. On slide 14, this chart is comparing clear key to protected key to secure key. So the first thing I want to point out is that your y-axis is not a linear scale, it's a logarithmic scale. So I'm pointing out here that secure key is significantly slower than clear key. With clear key, I could do 995,000 operations per second. With secure key, I can only do a little bit under 10,000 operations per second. So a pretty significant difference. But the other thing I want to point out is that as you, again, get out to those larger block sizes, performance is better. And especially comparing clear key to protected key. There's a significant difference for, it's significantly slower for a protected key operation with the 64K or 64 byte input block versus with a 1 megabyte block, the difference is almost nothing, 3508 versus 3442. So again, if you can block data and send more data, that's a good thing. The other thing to point out is that with protected key, I get much better security for my key material because with protected key, my key material is always encrypted. It just may not be encrypted or may not be protected by tamper-resistant technology. On slide 15, this is comparing the native instructions to APIs. So once again, what we're comparing here is a AES clear key operation using the KM instruction on the CPAC-F hardware, or against using the ICS-F APIs that will in turn invoke that same KM instruction. So at small block sizes, there's a pretty significant performance difference. But once again, once you get out to larger block sizes, the delta between and the overhead of going through ICS-F is spread over many more bytes of data. So it's much more efficient when you've got large block sizes. On slide 16, this is comparing, so the previous one was you comparing the number of operations. This is comparing the data, the megabytes of data that are being encrypted. And the same thing applies here. It's much more efficient. The trade-off is better performance with clear key, better security with protected key. And you have to look in your environment and decide what the right thing is to do. When I talk to customers about the choices, my recommendation is if you've got to have absolutely the utmost security, then you have to go with secure key technology. If you have to have absolutely the best performance, it's got to be screaming, then you want to go with clear key technology. But the reality is you get the best trade-off, you get the best cost versus security benefit when you're using the protected key technology. On slide 17, going back to the secure key, using the Crypto Express card, we saw earlier that with one job, we could do about just under 10,000 operations per second. What this chart is pointing out is that the Crypto Express cards are multi-thread capable. You can actually have up to 8 units of work passing through the card at a given time. So by multi-threading and sending more work to the cards, you can get better throughput on secure key at the cost of it taking a little bit longer. So the best example I have of this is way back when IBM first switched over to the CPAC-F technology. And actually, there was a customer running on the prior technology, which was called CCF. They had a job that was doing secure key encryption. They were actually encrypting their backups that were going off-site. And they were doing that on the old technology, and life was good and things were working well. When they installed their first Z990, that job that took about 4 hours normally, they had to cancel it after about 4.5 days because it hadn't finished. And the issue was that on the CCF hardware, that work was getting routed to secure hardware on the chip itself. When they went to the CPAC-F and the Crypto Express cards, they had this I/O operation going out to the Crypto Express card, and it really hurt performance. The way they solved the problem was by multi-threading. And that batch job that was encrypting lots of backup data, they just split it into multiple jobs and started running up to 8 jobs at a time, and they got back to an acceptable performance. So the point is the Crypto Express cards are multi-threaded, and you want to take advantage of that if you can. Try not to just have one application sending data to the cards or sending crypto work to the cards. Have multiple apps sending work to the cards. On slide 18, this is kind of this is comparing performance across multiple generations of KEX. And the point here is you probably want to be on the latest and greatest technology to be able to take advantage of the best performance. So you can see here that from the Z-EC12 to the Z13 and then to the Z14, there was a significant improvement in performance metrics and how much work you could get through the CPAC-F hardware. And IBM had to do that so they could support this thing called pervasive encryption and data set encryption. Now, with the Z15 and the Z16, that curve has flattened out and maybe even dropped a little bit. We'll talk a little bit more about the drop on the Z16 in a minute, but from generation to generation, there's going to be some minor variables, some minor variations in what you could expect. And then this is also just looking specifically at the CPAC-F hardware. We'll see on the next chart, we'll compare secure key and as well. So again, what you're doing in your environment, whether it's clear key, whether it's using the APIs, whether it's using secure key, and what you're doing. If you're talking up, in this case, we're talking about a encrypt operation. If you're looking at a financial ATM pin operation, the numbers are going to be a little bit different. The way this graph would look would be a little bit different for each of those. So the previous one was using a clear key operation. This is using an API. So it's got the overhead of ICSF involved. We still have a significant jump from the EC12 to the Z13 and the Z14. Things got significantly better, but ICSF is still involved, so it's not quite as good as using the native instructions. And then lastly, this is for secure key technology, again, a significant bump from the EC12 to the Z13. IBM was trying to make that encryption faster so they could support things like data set encryption. On slide 21, a similar chart for just 2 of the many ATM pin operations that are available. Performance has gotten better generation to generation. If you are still running an old non-supported machine, you can get some pretty significant performance benefit by upgrading those machines to current technology. And again, this is showing one operation at a time. On slide 22, we're showing the same APIs, but doing multiple operations, sending more work through the card. And again, because of the multi-threading capability, we can get a lot more work through the cards by multi-threading. On slide 23, so the last couple charts have been from that Z16 performance white paper that is currently not available. That document did not have this section in it yet. They're still working on it. So I've fallen back to the Z15 performance white paper to point out some things. And what this is showing is the SSL workloads that you can get through the Crypto Express cards. System SSL there are 2 phases in an SSL operation. The initial phase is called the handshake phase, where 2 parties authenticate to themselves. And we're using asymmetric encryption to do that. The record phase is where we're actually sending data back and forth in the network session, and that's using symmetric encryption. All of the charts that we've looked at before, those would apply to record phase. What this chart is looking at is strictly that handshake operation. And what it's showing here is that if you don't have any crypto hardware, then you're going to be using this second column to do the handshake. You're going to be using software. That is, System SSL has implemented RSA encryption using move characters and multiply and shift logical instructions. And when you're using just software on a Z15 with 4 CPUs running z/OS 2.4, you could get about 250 handshakes per second through those software engines. Now, that 255 handshakes per second is consuming 100% of those 4 general purpose CPs. So SSL operations are very expensive in software. If you install a Crypto Express card, Crypto Express 7 on your Z15, and you have ICSF up and running, now you can get over 10,000 handshakes per second through the system. And your CPU usage drops to a little bit less than half. So you're only using about 2 of those CPs, meaning the other 2 CPs are available to do real work, other things that you need to do. Now, when you're doing that, you're driving that Crypto Express card at about 99% utilization. But the point here is having Crypto Express cards can help significantly with SSL handshakes. If we convert that coprocessor to an accelerator, remember that an accelerator, you only have 3 APIs, public key decrypt, public key encrypt, and digital signature verify. But those are the APIs that are used in a system SSL handshake. And by converting to an accelerator, I can get a little bit over 13,000 handshakes per second. I'm driving the CPU a little bit harder to get that work to the cards. So I'm using a little bit over 2 of the CPs. And that card is running almost flat out, but I do get a bump in performance or throughput. Lastly, this chart doesn't call it out real clearly, but in this column, what we're doing is both client and server authentication. So we're doing twice as much work. By default, the system SSL protocol requires that the client authenticate. Optionally, that the server authenticate. Optionally, you can have the client authenticate as well, and that's what this chart is showing. So we're getting a little bit more work through by adding a second accelerator and just giving it a little bit more capacity. Now, quickly, I'll mention the avoid it system SSL. You have to go through the handshake operation once in software or hardware. But once you go through it once, system SSL will cache that information. And if you need to re-authenticate later, you don't have to go through these engines to get the work done. And obviously, the throughput is going to be much, much better when you do that. But again, the first time you do a handshake, you've got to use one of these technologies. Now, I want to point out on this chart that on the Z15, if I have a coprocessor, I could do just under 11,000 handshakes per second. If I convert that to an accelerator, I can do a little bit over 13,000 handshakes per second. So roughly a 25% improvement by converting a coprocessor to an accelerator. On slide 24, I'm showing the same information, but on a Z13 with Crypto Express 6 cards. And what I want to point out here, or I'm sorry, Crypto Express 5 cards. What I want to point out here is on the Z13 with those Crypto Express 5 cards, if I had 4 cards installed, I could do about 20,000 handshakes per second. That works out to about 5,000 handshakes per card. If I converted those coprocessors to an accelerator, it only took 1 accelerator to do over 21,000 handshakes per second. So my point is that on this older technology, there was a much bigger bang for the buck if you convert it from coprocessor to accelerator. You got 4 times as much throughput on an accelerator versus a coprocessor. On the Z14 and on the Z15, those numbers aren't quite as dramatic. I don't have an explanation of why, what IBM did within the hardware, but my point is that the consideration for converting a coprocessor to an accelerator is much less compelling on the current technologies. It still will give you more throughput, and if you have a requirement, if all of your crypto work is network handshakes, it may be worth considering converting those accelerators, but it's just not quite as compelling as it was on earlier generations. On slide 25, talk about QSA. The Z16 announcement letter specifically called out and says that the bulk of the performance improvements on the Z16 crypto were related to QSA. And very clearly, we can see that up at the front of the chart, these particular operations, there's a pretty dramatic improvement in QSA operations. Now, some of the others, the performance isn't quite as dramatic, but there are still, the Z16 is better performing when it comes to QSA. Now, I don't see a lot of people exercising QSA yet, but clearly that's coming. There's a lot of focus on that, and the Z16 is going to give you better performance when it comes to the quantum safe algorithms. So that was a discussion of the metrics, what you can see on your hardware. The next couple of slides are going to talk about some of the performance reporting that's available. The first capability is the CPU measurement facility. If you're running HIT, the HIS started task, the hardware instrumentation services, one of the things it can capture is the number of crypto operations that are executed on the CPAC-F hardware. Now, they're broken down into buckets. There's a pseudo random number generation counter. There's a SHA counter for SHA hashing. There's a DES counter, AES counters, and then on the Z16, the elliptic curve counters as well, because those operations are available on the CPAC-F hardware. I would, going back to my earlier comment about knowing what your normal is, I would suggest capturing this information and looking at trends over time. As you roll out things like data set encryption, you should see these AES counts going up because you're going to be doing more AES work. And depending on what else you've got going on in your system, you may see some of these other numbers trending upwards. And you probably at least want to look at those trends and monitor those trends and look for anomalies as over time. On slide 27, there is an RMF crypto hardware activity report that's available. What this will provide, and this report spread over a couple pages because there's a lot of information in this report. It's broken down into 4 sections: for the CCA coprocessor, for the accelerators, for the PKCS11 coprocessors, and then there's an ICSF section. Now, what this shows, and going back to ZOS 2.3, you did not get the breakdown by LPAR. So with ZOS 2.4, they started including this breakdown by LPAR. But what's the important field on this chart, as far as I'm concerned, is the utilization across the KEK. And what we can see here is that these Crypto Express cards are running pretty hot, and it might be time to add a card. Now, I'm going to point out that they do report on the number of keygen operations. I'm not sure what value there is in knowing that, but certainly I would be capturing that and monitoring it as a trend. And I'll come back and touch on this again in a minute. The next page of the chart shows the same information for the PKCS11 coprocessors. Again, the important number as far as I'm concerned here is the utilization of the card. This Crypto Express card isn't running that hot. Well, no, I'm sorry. It's this column here, the 99.9, and it is running pretty hot. Now, this chart does provide a breakdown by type or by function: asymmetric fast, asymmetric gen, asymmetric slow. But unfortunately, IBM doesn't document what falls into each of these buckets. So I'm not sure how useful this information is. The third section of the report is on the accelerator and what work is going through the accelerator. Again, looking at the utilization of the card, this accelerator is running kind of hot. Might be time to add some more resources. Now, with the accelerator, we do provide a breakdown by key types. So RSA, modulus exponentiation, or Chinese remainder theorem, and then the key links. And we can see the breakdown of the workload. If we had this information for the coprocessor, that might give us a clue as to when it would be worth considering converting a coprocessor to an accelerator. But unfortunately, this information is only available on the accelerator. And then the last section of the chart is for ICSF services. This is pulling some information from one of the ICSF control blocks. Again, it's just sampling some various fields. If you care about AES encryption, then you probably want to look at these numbers. The one thing that I'll flag here is obviously they're still doing single DES encryption, and I've got to ask why. Nobody should be using single DES encryption at this point. It is no longer considered secure. And then some of this same information is available real time via RMF Monitor 3. Starting with ZOS 2.4, there are 3 commands that you can enter in Monitor 3 to look at the crypto hardware overview, which gives you coprocessors, accelerators, and EP11 cards. Or you can focus on the accelerators or the EP11 cards, and you would see very similar information to what we just saw in the crypto hardware activity report. It would just be a real-time snapshot of what's going on in any given instance on your system. And then lastly, I want to point out the LACSCR report. This was implemented so you can start measuring data set encryption. This is measuring the long-term average of CPU service consumed by data set encryption. So as you start ramping up your data set encryption, you're probably going to see these encrypted MSUs trending upwards. And once again, I would be looking at these to look at trends over time. And, you know, most customers, we heard earlier, most customers are still testing it, prototyping it. And what you're going to see here is these numbers are going to start out very low. And then when you start encrypting 2 or 3 data sets, you may not even budge the needle at that point. But when you start getting serious about data set encryption, and maybe you encrypt your first 100 DB2 databases, I would expect to see these numbers jump up. And then you might run for a while just encrypting those 100 DB2 databases, and then you might do 100 more, and you're going to see another jump. And what you should see is those encrypted MSUs trending upward over time as you roll out data set encryption. So kind of summarizing things, there are performance metrics available, but they're somewhat limited in what they can tell you. And one of the issues here is, IBM's got to, how much performance data do I make available? Because if I start presenting information, hey, we're doing all AES encryption, an attacker can target their attack. Hey, we don't have to worry about things like DES encryption. They're not doing any of that. So providing performance metrics without providing some side information to enable an attacker, it's a tough, where's the right boundary here? You should look at, you should monitor your performance, look at that RMF hardware activity report, look at the CPU measurement facility. And in the earlier presentation on network encryption, he called out using the CSF stats. I think that's a great idea. You should have CSF stats turned on. You should be capturing those metrics, but then you're going to have to use some of your own tooling, SAS or Mix or whatever, to process that data and report on engines and algorithm usage. The performance metrics are getting better. I think there's still some work to be done at IBM. I think they're working on it. We just got to wait for it to come out. There are a bunch of red books that are still available. All of those are somewhat dated. They're still accurate for the most part, but they're old and out of date. If you want to look at performance metrics, you want to probably start with those RMF reports. You want to look at the SMF data that's available, maybe generate some custom reports to look at some of the SMF records. The crypto performance white papers. I've got this Z16 one. Again, it was published briefly at this location. It's since been pulled back. That's why it's grayed out. But you still should be able to get the earlier KEX if you want to look at the white papers for the earlier versions. I did not talk about this ZOS communication server performance. every time IBM comes out with a new level of ZOS, the ComServer guys do some benchmarks and report on ComServer interesting stuff. Some of those reports will include crypto information as well. So it's not every generation of these reports that covers crypto, but some of them do. You may find some useful information there, especially if you're worried about network crypto performance. So with that, we'll open it up. I have not been monitoring the chat. So Jamie, I don't know if there's any questions.
Just having a just trying to catch up. And there's thing in the chat. Any questions for anybody in the room or online as well? You can post your questions. Lenny, you must have something.
Yeah, I would expect Lenny would.
By the way, while Lenny's walking up towards the microphone, there's plenty of stats. I see Greg to keep the CPU police busy. CPU police and organizations, that is, that are interested in these things.
Hi, Greg.
Yes, sir.
On the charts where you showed the performance of various things across the different generations of Z-series CPU, did I miss something, or did I see that the performance went down on the later CPUs very slightly?
Yes, you did. I don't have a complete explanation of why. If you go into those documents and zero down and really look in detail, you will see anomalies here and there. There are cases where 64 byte block and then a 128 and 256 and everything's looking normal, and then all of a sudden there's a drop, and then for 1 meg it goes back up. I have never been able to get an explanation for that. More generally, the Z14, there was a lot of work done to get to the Z14, and performance got better. My best explanation of why there might be a little bit of drop off from Z15 to Z16, especially on the Crypto Express cards. The Crypto Express cards are running their own operating system. They're running their own application on that card. And as you add more functionality, obviously there's a little bit more overhead in terms of, okay, what's the right path to go down within this card? So that's my best explanation of what's going on, is as they add functionality, that has an impact on the branching they have to do to figure out what path to send you down, and there may be a drop